2,
okay,
hello.
Great.
We're good.
Okay, so everyone, Hansol Suh is a researcher at Argonne National Laboratory. He's been working with me for a while on many different approaches to optimization, with an interest in smooth and non-smooth problems. We had a fun project working on improving BFGS, and he's going to tell us about the thing. Hansol, go right ahead.
Okay. Hello, everyone. Okay, so thanks, Toby, for the introduction. So my name is Hansol, and I work at Toby at Argonne National Lab. And today I'm going to talk about the dense BFGS method that we recently implemented on PETSc. And then, okay, so I'm going to do a brief recap and overview of what BFGS is, and then explain what we mean by dense BFGS and some benchmarks and results. Okay. So, this is a very, I'm sure most of you are familiar with the quasi-Newton method, but I'll just reiterate it for the better explanation in the later slides. Okay, so for quasi-Newton optimization, you have a gradient of some convex function or whatever, and then, so I have some matrices B, so we update the current iterate X and G into this matrix, and then you solve. So you give G and then pop out P, and then you somehow find this alpha, the step by line search or whatever, and then you update your next iterate. So this is a canonical representation of a quasi-Newton. And so what is this B here in PETSc? Okay, so B basically approximates Hessian matrix in a quasi-Newton method. So in PETSc, that would be a MET-LMVM, where LMVM means a limited memory variable metric. And MET-LMVM is used in SNES-QN, PC-LMVM, Tau-LMVM, and etc. Okay, and these are the list, few of the list, not all, of the MET-LMVM methods in PETSc. Okay, so BFGS means Broyden-Fletcher-Goldfarb-Shanno, and then DFP means that. So so previously the BFGS and DFP are well known, and then they have SPD property. And then today I'm going to talk about the dense. Okay, so there's a D. Okay, dense version of BFGS and dense version of DFP, and then dense QN, which is basically a hybrid of these two, which obviously also share the SPD property of BFGS and DFP. And then also, side note, there is a SR1, which is a symmetric rank 1, which is has a symmetric property. And then there's a Broyden, and there's other Broyden, like bad Broyden, which has a square if you need your Hessian to be square or symmetric. So, so those are the MET-LMVM current implementations. And then I'll talk about what is actually a DBFGS. Okay, so BFGS, it approximates Hessians using past iterates and the past secant conditions. Where I mean by secant condition is something that satisfies this condition, where your matrix times the difference in your current and previous iterate equals to a difference in gradient of your current and then previous iterate. And to get this Hessian inverse, this is a canonical representation where, so you start from the B0 and then iteratively go up until K plus 1, and you do this bunch of dot product. So it'll be you're doing 2 rank 1 updates iteratively. So it'll be 2 rank 1 update times K plus 1, starting from B0. But obviously, you don't necessarily want to do the full history, just like in SNES Anderson. You don't really do the full history because you only, your memory would blow up, and then empirically, you only 5 or 10, maybe 20 history size is perfect, good enough for most cases. So so limited memory means instead of starting from B0 to K plus 1 all the way, you have a B0, but you only do K plus 1 minus M, where M is a history size. Okay, and even though you do only use the past k minus m iterates, there is still B0, which is an initial guess. So either there are options built in right now. It's a non-scalar diagonal user, or decide. Okay, none is basically identity, nothing. Scalar is a scalar times identity, and diagonal is a diagonal matrix, and user is user. So that usually means some sort of an initial guess about your problem, or some previously known information about the problem or geometry of the problem you're trying to solve. And okay, and I will denote the classical implementation that you probably saw in the introduction to optimization class as a recursive BFGS. Okay, so this is a classical BFGS, which I call recursive in this presentation. Okay, so the big thing that you need to notice here is that, okay, there are two for loops, okay? And then we are doing a for loop over and do a bunch of dot product and XP. And then do solve on the initial guess, and then do another for loop over the dot product and then another XP. Of course, you can cache this in actual implementation, but I just put it there for easier understanding in this pseudocode. So as you can see, there are a lot of level 1 BLOS operations here. So that'll be k minus m times dot plus XP, and then same for the second for loop. Okay, so yeah, there's a lot of sparse BLOS level 1 operations, and that it has a rather poor memory movement pattern. And it can be very suboptimal for GPU because it requires a very frequent synchronizations and then kernel launches. So if you do run this algorithm and then profile it in the GPU and PETSc, then you'll see that most of the time is actually not done on computation, but waiting for either kernel launches or synchronization. So it's rather inefficient for GPU. Okay. So then I'll talk about dense BFGS. Okay. So what I mean by dense BFGS? Okay. So like I said before, because of its inefficiency, we don't want to iterate over a list of vectors with the level 1 BLOS. But instead, we can turn the data into matrices and then do as much as level 2, 3 BLOS as possible. Simple in theory, but it can be rather tricky because you can't really store them in the historical order. In vectors, you don't really care because you just need to maintain the indices. But for matrices, you can't do a historical order because if you want to store in the historical order, that would be order m times n every time you update it instead of order n when you do store in non-historical order. So I'll call that a cyclical order where instead of, okay, you have a 0, 1, 2, 3, 4, and then for the 5, you do 5, 1, 2, 3, 4. So that I would call that cyclical order. So for just generic GenV operations, whether it's a cyclical or historical, actually doesn't really matter. But for triangular solve, it does matter, as you can, I will show in the next slides. Okay. So this would be your history of a difference in your solution vectors. So like I said, okay. So 0, 1, 2, 3, 4, but okay, now you're moving on. Okay, then it'll be 5, 6, 2, 3, 5, 6, 2, 3, 4. And then GenV actually doesn't really matter. But okay, let's think of a matrix R where it's a S transpose times Y. But what if I need a triangular solve on Y, but in a historical order? Okay, so what I mean by H tri U is a upper triangular in a historical order. So imagine you may turn it into historical order and then multiply it against and then see how it's actually represented on the memory. This is how it looks like it. So yeah, essentially, if in a real historical order, this guy would be here. So then you have a real triangular matrix, and then you can do one triangular solve. But you can't do that here. So here you have to do two triangular solve and one GenV to do a triangular solve. So that would be the cost of maintaining a cyclical order instead of history order. So dense BFGS algorithm requires you to have a R matrix, which is R transpose Y. As I showed in the last slide, and the algorithm requires you to do a triangular solve on this upper part of R. And because S and Y are in the cyclical order, R is also in cyclical order. And instead of doing one triangular solve, we get two triangular solves and one GEM-V. Okay. So this is the algorithm of dense BFGS. It probably doesn't make too much sense right now. I'll do a more graphical illustration next slide. But what you need to see is that, okay, there is no for loop. And then most are GEM-V and then triangular solve operations. So a bunch of level 2 batched operations. Okay, so, and then you have one triangular solve here and then another triangular solve, but on the transpose of it. Okay, so what does this actually mean? Okay, this is a block matrix format of this previous one. So when you write this out, this becomes this. Okay, so this is a simplified, this is the recursive BFGS algorithm that I showed you in the beginning. And I denote R as a historical order of STY and then D as a diagonal of it. Okay, so looping over this part is this dot product and all reduced becomes just one GEM-V and then one triangular solve in historical order. And then the looping over the XP becomes just a batched operations with the GEM-Vs over there. Okay, and then solving for B0, that's the same. That doesn't really change. Okay, and then looping over the last part just becomes a bunch of GEM-V operations and one additional historical triangular solve or cyclical triangular solves. So this is the gist of dense BFGS. You turn a bunch of for loops and then turn them into a bunch of batched level 2 BLOS operations. So yes, okay, you lose. There's a little bit more memory overhead because you have more things to keep track of, like R matrix here. But on the flip side, you don't you minimize this on synchronizations and kernel launches, especially for GPU. If you think about the throughput. Okay. But if you are aware of the history of a BFGS, you may ask, okay, wait, hasn't the dense BFGS has been around for a while? Which is, yes, that is true. So the original dense BFGS paper was introduced by Broyden-Fletcher-Goldfarb-Shanno in 1994. And okay, this is their version of a dense batched version of BFGS. Okay, one thing to note here is that there are, how many H0 are there? Okay, there are 1, 2, 3, and 4. And then H0 has a YT, H0, and Y. So you can see that if your H0 is something other than identity, then you have to, there's more additional works that needs to be done. So for illustration, okay. So this one, our version, there's only one H0, right? So whether H0 is a diagonal or identity, scalar, diagonal, or whatever, you just do it once and that's it. But the Broyden-Fletcher-Goldfarb-Shanno one, there are 4 of them there. So yeah, so if H0 is some variable, something changes, then for their version, you have to do extra M evaluations where M is the history size of the H0. And if it's just a constant or scalar H0, then you still need to do 2 more level 1 BLOS calls. On the flip, but our method avoids this. So that would be improvements from the Bird's novel version from 1994. Okay, so I'll do a side-by-side illustration for the of the recursive and dense formulation. Okay, yeah, just going over what I did on the block matrix format, but this on the side-by-side with the algorithm. So maybe this makes sense. This makes more sense. Okay. This ST, so this W is a copy of G for work. So that part is done there. Okay, so dot product turned into GemV, and this YTSI is turned into a triangular solve historic. So that'll be one GemV and then two triangular solves. And then this XP is turned into GemV. And then, yeah, the B0 solve doesn't change. And then, yeah, in recursive case, like I said before, this guy will be cached. But you can't do that here because you have to solve it again because it's how it works out. But regardless, recursive one is a looping over dot product and XPs. And the dense one, you just have a bunch of GemV and then triangular solves. Okay, so here's the so recursive one. There are way more BLOS, about roughly 10 m times n BLOS, level 1 BLOS. Whereas for dense, we only do 2 times n, and then we do more level 2 BLOS operations, 4 times m times n. So recursive has just all reduce, but the dense has a 3 reduce and then 2 broadcast, where 2 means if it is B0 is a none, so identity, then you can get away with. But anyway, so instead of doing all reduce for recursive, for dense, we do the reduce and broadcast. Okay, so far everything is for solving. Okay, but what about mult? Okay, so this is the for dense representation we have for BFGS. This would be the block matrix representation of a multiplication. Yeah, notation is kind of convoluted. Okay, but you have to store the B0 times S, and then you have to store that multiply against S, and then you have to store this times the lower triangular, not upper triangular, but S transpose Y. And you have to do a Jacobian, Cholesky factor of this guy. So that is the one downside about dense BFGS algorithm is that you have to do Cholesky. So, as you can see here is m by n. So typical BFGS history size 5, 10, at most 20 usually. So this is 20 by 20 Cholesky factorization. But because of how the implementation is done, also because it's small, let's say you are working over multiple GPUs, what we do is that only the rank 0 GPU will be doing the Cholesky, and then everyone else would just be using from the rank 0 GPU's Cholesky factorization. So yeah, it's not that memory intensive in that because it's only about m by n size, but still you have to do Cholesky. So that would be the downside of MATMULT about dense BFGS. Okay, yeah. So MATMULT dense BFGS require Cholesky factorization, and then there's a little bit tricky. So if B0 is an identity, yes, the Cholesky is proven to exist for every time. But if B0 is not identity, sometimes the Cholesky can be unstable, and then the default Cholesky and PETSc may crash. So it doesn't. What's the error message? I don't remember what the error message. It says.
Pivot error.
Yeah, you get the 0 pivot error and then just crashes. Yeah. So to avoid that, unfortunately, our default implementation of MAT-LMVM dense BFGS is to use just the classical recursive one where you loop over the level 1 blocks. But if you want to use, if you know that Euler-Cholesky is the state, Euler-Cholesky will exist because your B0 is none, then okay, you can use this flag option to say, yes, I actually want to use recursive for our MAT mult. Okay, and then there is, okay. I talked about MAT mult, but in the beginning, you may have noticed I talked about the DFP. And, okay, so there's a DFP, and DFP is a dual to BFGS. So what does that mean is that BFGS solve is more or less equivalent to the DFP mult, and then DFP solve is more or less equivalent to the BFGS mult. So we have this implementation called MAT-LMVM dense quasi-Newton. So this guy, so BFGS mult has Cholesky. So on the flip side, DFP solve has Cholesky. But okay, what if we don't use the Cholesky version, only use the good side? Okay, so this guy doesn't have Cholesky and this guy doesn't have Cholesky, and they're all level 2 blocks. So that's what we call by dense quasi-Newton. So in theory, that should be the fastest. But but there is some duality gap because okay, if you multiply BFGS solve times BFGS mult, it should be identity. But if you do it with these two, then it's not quite the same. So there is some sort of duality gap. So you need to be mindful of that. So so this is the side of a dense BFGS or dense LMVM that you need to be mindful is that how much of your operation is going to be MAT solve or MAT mult. For generic quasi-Newton, if you know that everything you're going to do is a MAT solve, then sure, great, just use a BFGS. If in some sort of a trust region things where you only need to do a MAT mult, then okay, then you should use DFP. If you use both, then you need to be mindful of how much of solve am I doing, how much of a mult am I doing. Do I need to be really, really stable? Then okay, then you use a recursive. And if I just need to run fast, then maybe you can risk it with the dense QN. So yeah, that would be something a little bit more, something that you need to be more mindful of compared to using classical BFGS that's in PETSc. Okay. These are some benchmarks. Okay, so it's in the KSPLMVM test right now on the main. That's the main. It's a pretty simple. Okay, we set some history size, and then okay, you update it, and then you iterate over some sort of vec xp, and then vec on the x, and then g, and then you push it into your LMVM matrix, and then you just solve it and iterate over. Yeah, nothing special about this. Very.
The point is that it's testing, you're timing just the quasi-Newton update, not the user's actual logic for evaluating the objective or the gradient. Yeah.
Yes, precisely. Yeah. If you were to just say some quasi-Newton method on something, it's gonna time everything else that's not just BFGS. So the timing improvements on the dense BFGS kernel maybe get lost by other things. So this is just to make sure that we only time the BFGS kernels to see how much improvement we got. Okay, so I ran it on both Polaris on ALCF and then Frontier on OLCF, and then okay. There's a simple 1 MPI process on the Polaris, on the AMD. So N is the problem size, and then the square size is your size of history size, 5, 10, 20, 50. And then, okay, 10 times 2, 3, 4, 5, 6. So it's a bigger problems. And then the Y scale is effective bandwidth of the problem. And so as you can see, except for this case, all the other, so our pink or the purple one is our dense version, and it's almost outperforms the recursive version. And this is almost overlaps that's when everything just lives on the memory nicely, on everything on the cache. So there's not much benefit gained by minimizing memory movement, because there is no memory movement in that case. But every other cases where memory movement is actually important, like the biggest one, you can see almost like 70%-ish improvement on 1 MPI core on the CPU. And then on the right-hand side, we have 8 MPI ranks, where 1 MPI rank for one chunk of L3 cache. We see a very similar phenomena, where everything lives on this memory, then it's very similar, but everything else, you see a significant, so this guy maps to this. So you have roughly 70% plus improvements in the effective bandwidth. Okay, this is for OLSIF Frontier CPU, pretty similar. This guy overlaps on the 8 MPI and on Frontier, but it's a little, okay, 10.7, okay, a little bit better here. So, nothing more to say on the comparison between Frontier CPU and then Polaris CPU. Just even on the CPU, even though this was designed with the GPU implementation on mind, still works very well for the CPU version. And then, okay, so this is a Polaris GPU. So they use the NVIDIA A100 GPU. So left is a 1 rank. And then Polaris has a 4 GPU per rack. So that'll be a 1 node allocation. So, okay, what am I saying? Okay. You can see that I think this was some sort of issue with the Polaris's CUDA kernel. So you don't see this on the Frontier, but regardless, you can see that the roughly 50% increase in effective bandwidth for the largest and biggest problem case for the one GPU, and then for 4 GPU, it's almost more than double for the biggest problem size for the NVIDIA A100. And then, okay, and then for Frontier, this Frontier has 8 GPUs per node, and then a little bit more memory. So we didn't get to do the 10 to the 8 on the Polaris A100, but we could do this on the Frontier. You could see that, yes, on almost 100% improvement on effective bandwidth on 1 GPU, and also on the 8 GPU case for the Frontier AMD GPUs. Okay, so to summarize, okay, we implemented a dense BFGS for quasi-Newton. It'll be a MAT-LMVM DBFGS, and then it's just faster and more versatile it's fast and versatile for both CPU and GPU. Even though we had GPU improvements on mind, it turned out that it works also very well for CPU. One caveat, like I said, is that mult had Cholesky. So default implementation is a recursive one. So if you need a lot of fast mat mult, then you may want to consider DFP if needed. And if your mat mult and mat solve is 50-50 or something like that, then you may want to consider DQN, where we use a BFGS for solve and DFP for mult. But there is a duality gap, so you need to keep that on mind. And I didn't put it here, but we also put some more general improvements on existing recursive method, not just for dense ones. So even the existing one have a little bit more of improvements by the better layouts and whatnot. So yes, that is it. Thank you.
All right, we've got time for a few questions. Any questions for Hansol? Barry?
In the cases where the Cholesky gets its 0 or negative eigenvalues, when you use the recursive approach, everything works fine. Is that correct?
Yes, the recursive one is not. So recursive one kind of looks like, well, this is for BFGS, but recursive BFGS mult looks like this. So there's no.
So the thing is that recursive BFGS mult has a setup to make it look like that, but it has to first compute the basis that makes it look like that. And so the recursive approach more or less computes the output of multiplying the Cholesky factorization by a basis in a for loop. If you just go back to the slides that show the dense form, there we go. So it's sort of like the recursive version more or less computes a symmetric factor of the inner matrix multiplying the y and the p0 as it goes along. We didn't get to there actually is an asymptotic improvement in that that approach is going to, because it's got sort of a double loop and it's all vector logic, is going to be order m squared n work. And this, because we do the Cholesky factorization, changes that to order mn plus m cubed. And m is the small variable and n is the big variable. So when it works with the Cholesky factorization, and I think we may get that worked out, it's also an improvement.
So is the recursive approach by guaranteeing a symmetric positive definite application, or do you lose that when the Cholesky fails?
No, it's guaranteeing symmetric positive definite. The failure mode that I think that Hansol has seen is actually not just it's a combination of both B0 and essentially having repeats in the S and the Y matrices. It's pretty. I don't think we have it entirely figured out yet. Okay. Anything else? Yeah.
I understand the Cholesky is only 20 by 20.
Well, yeah, if your history size is 20, yes.
History by history. Is it obvious that the GPU is going to be faster than the CPU for that size of matrix?
It's not going to be faster, but there's also really not a whole lot of so the inner products that we're computing, like so we're doing a factorization on F. The main thing is the F circle part, F naught. That's already living on the GPU. So even though it's kind of silly to do Cholesky on the GPU for something that's small, the alternate is move that data to the CPU and do the Cholesky and move it back, and they're not a big deal. Yeah.
Since you have performance result with the CPU and the GPU on Polaris and Frontier, so how much was it faster with the GPU over CPU?
Okay, so we can read. Yeah, okay. So Frontier.
You can just read the vertical. The y-axis is just a linear scale.
Yeah.
So it depends on problem size and history size.
Mm-hmm.
So go to the GPU ones. So like for the biggest problem sizes, you're getting essentially twice the effective bandwidth. For the big problems, you're actually much faster for the smaller problem sizes, simply because the reduction in the number of kernel launches. Like you can increase the history size, and you're not actually increasing the time that much. Whereas for the recursive version, you're just increasing linearly the number of kernel launches. It doesn't show up very well on the vertical bandwidth because neither method is getting good bandwidth. But in terms of latency, it's a big improvement. Actually, like order of magnitude improvement. Yeah.
So it'll be 200. Well, 100 for the biggest case for 8 MPI.
Are all these with identity?
Yeah, these were all where B0 is the identity. Yeah.
We're excited to try this out for discrete gradient, where it's not going to be the identity. It would be interesting.
Yeah. All right, let's thank Hansol one more time, and we'll let our next speaker.